Papanyan Ananth and Rolando La Placha, and Papanyan will be giving the talk. It's
Great.
your stage.
Okay, thanks, Dominique. So I'm going to talk about secure software leasing, and this is in joint work with Rolando La Placa. Oops. So the starting point of our work is the no-cloning theorem of quantum mechanics, which says the following. There does not exist any universal cloner that, given a state, produces two copies of the state. While no-cloning theorem might come across as a disadvantage of quantum mechanics, it is quite useful to build many interesting cryptographic primitives. One such popular example is quantum money, which says that you can associate digital money with some quantum state such that you cannot produce many copies of this state. So this is useful for preventing production of counterfeit digital money. So this no-cloning principle is also employed in the context of unclonable encryption and one-shot signatures and digital signatures. So the topic of this talk is going to be using this no-cloning theorem to prevent illegal distribution of software. In other words, we are going to talk about the notion of quantum copy protection. So here is a problem. A software vendor, is selling software to the users, and software vendor wants to make sure that the users don't illegally distribute the software to other users. And if you just want to use classical technology to solve this problem, it's not going to be possible because if a software is represented as a binary string, it can always be copied. So natural question is whether we can use the no-cloning principle to solve this problem. And Aaronson came up with the notion of quantum copy protection precisely to address this problem. So let me explain this notion with an example. So suppose, let's say, Microsoft wants to copy protect some software. So what it does is it starts with some circuit that represents the software. It compiles the circuit into a quantum state denoted by rho c. And along with this rho c, it also sends some evaluation algorithm to the user. So the user can compute C of x on any x by using the evaluation algorithm eval and rho c. Okay. So this is the functionality of copy protection. In terms of security, what we want is that a user should not be able to produce two different copies such that both these copies have the same functionality as C. So here I'm considering the case where the two states the user produces are unentangled, but you can suitably formalize the notion where the output states are entangled. So we want the user, the success probability of the user to produce two states so that both of them compute the original circuit. This success probability should be negligible. Okay, and you can think about many unclonable primitives like unclonable encryption, one-time signatures, and so on. So all of them can be thought of as copy protecting very specific functionalities. Okay, so what do we know about copy protection? So far, we know how to construct copy protection for unlearnable functions in the Oracle model, quantum Oracle model. Recently, this was improved to classical Oracle model. And we also know how to construct copy protection for very, very specific class of functions like point functions in the play model. And however, this construction was also just heuristically proven to be, it was heuristic, meaning that it was not known how to base it on a concrete cryptographic assumption. So natural question to ask is whether you can construct copy protection for all unlearnable functions, and this was open since Aaronson's work. And in this work, we show that the answer is no. And this is a conditional result because we are going to base it on some cryptographic assumptions. So we show that copy protection does not exist for all unlearnable functions, assuming fully homomorphic encryption for quantum computations, and also LW is hard against quantum polynomial time algorithms. So specifically, we identify a class of functions that is quantum unlearnable, and then we show that if I give you a state that computes this function, then you can create multiple copies of this function. Okay, so we showed that for all learnable functions, it's impossible. So a natural question to ask is whether you can identify maybe a simpler class of functions and try to construct copy protection for them. For example, we can focus on evasive functions. And this seems like a very hard problem. We don't know how to construct copy protection for evasive functions. So instead, what we are going to identify is that there are settings where you don't need the full power of copy protection, and you can settle with weaker notions. Specifically, you can consider a weaker setting where the evaluation algorithm is fixed, right? And the adversary has to output a state with respect to that works with the same evaluation algorithm as dictated by the software vendor. So towards this, we are going to introduce the notion of secure software leasing. So there are two security notions associated with secure software leasing. In terms of functionality, by the way, secure software leasing is the same as copy protection. So what is different is in the security notions, which I'm going to talk about now. So there are two security notions you can consider. One is infinite term lesser security, which says that the adversary cannot produce two copies that both compute C with respect to eval. And the second one is finite term lesser security, which says that after the adversary returns back the copy he had that was given to him by the software vendor, he should not be able to produce another copy that still computes the same circuit C as before. And what we show is that even finite term SSL doesn't exist for all unlearnable functions, and this is based on the same assumptions as before. And we show that in terms of positive result, we show that infinite term SSL exists for evasive functions. And this is based on sub-exponential hardness of QLW, post-quantum indistinguishability obfuscation, and post-quantum input hiding obfuscators. These two are some notions of program obfuscation that I'm not going to talk about now. Okay, so in the remaining, I don't know how much time I have. Okay, so in the remaining time I have, I'm going to just quickly highlight the challenges in the impossibility result and also the positive result. So the main insight that we're going to draw from in the impossibility result is from the similar result of Barak et al., who showed that there exists a class of functions, there exists a class of circuits, such that if I give a class, if I give a physical description of this, of any physical description that computes this circuit, then you can extract some secret S out of it. On the other hand, if I give black box access to this circuit C, then you'll not be able to recover the secret S. And why are these two useful for ruling out copy protection? So we can look at bullet one, and maybe we can use the ideas there to recover another implementation of C, right? So instead of recovering a secret, maybe if we can tweak the techniques and get another implementation of C, we are done, right? And from bullet two, maybe we can use it to prove unlearnability of the circuit, right? So it seems like these two bullet points given to us by Barak et al. Seems useful. Okay, but there are some challenges to sort of make this work in the quantum setting. There are two challenges. The first challenge is that in order to rule out copy protection,
Can you
have to. Sorry.
Can you please try to wrap up?
Yeah. This will be my last slide. So the main challenge is that, you know, given an implementation of C, you need to recover not just a secret but another implementation of C, right? So that's the first challenge. The second challenge is that implicitly in the Barak et al.'s argument, you're using the fact that the evaluator can make many copies of the software. And in the quantum setting, this is sort of hard to do because of the no cloning theorem. Okay. So with this, I'll conclude. Oh, yeah.
Okay, thank you. Thank you for the talk. I think we have to proceed to the next speaker right away because we are slightly behind time. So Alex, please, do you have your slides already there? Okay, thank you for your talk. So the next talk will be given in person by Alex Grillo. It is about Oblivious transfer is in mini QCrypt by Alex Grillo, Hui Tia Lin Fang Song, Vinod Vaikuntanan. Okay. Oh, where's best button?
Okay, thanks for an introduction, Dominic. So yeah, as the title says, we are interested in having quantum protocols for Oblivious transfer. And let me just quickly recall what Oblivious transfer primitive is. So we have two parties, the sender and the receiver. The sender chooses two messages, M0 and M1, while the receiver chooses a bit B and learns the message MB and nothing else. And it is well known that OT is fundamental in cryptography, and in particular, it implies general multi-party quantum computation, general multi-party computation. We know that classically, OT can be built from public key encryption in general, but the result of Impagliazzo and Hudich tell us that OT cannot, we don't expect OT to be built from one-way functions in the classical world. But quantumly, around 30 years ago, Crépeau and Killian, and then VCDS, they proposed protocols for OT, quantum protocols for OT, which are based on commitment schemes. So this gives us hope that they would be able to have quantum OT from one-way functions. But later results that prove the rigorous security of these protocols actually show that we require a strong security notion for the commitment schemes. And these commitment schemes with strong security guarantees we don't know how to construct them classically only from one-way functions. The main technical result of our paper is to show that these commitment schemes with strong security guarantees, they can be built quantumly from one-way functions. And in particular, this tells us that, oops.
You might be able to hide it when you click on more.
Oh.
Like floating meeting control.
Down. Oh, perfect. Okay, great. So in particular, this shows that OT and in general MPC, they are mini QCrypt, which is like in parallel to Impagliazzo's 5 world, is the world where you have access to quantum resources and one-way functions. And I'll try to give an overview of how we can achieve these strong commitment schemes and in particular OT from quantum one-way functions. And to start with, we have used Nauer's commitment scheme, for example, with zero-knowledge proofs. And we show that we can build equivocal commitments. And then using these equivocal commitments in these protocols, quantum protocols for OT already gives us some weak notion of OT, where it's OT with unbounded simulation. Then we can use this unbounded simulator OT together with Garble circuits to construct what we call unbounded simulator verifiable conditional disclosure of secrets. And finally, from this unbounded simulator VCDS, we can show that we can construct extract commitments and therefore OT and MPC. And I think that the main part of our result is having this verifiable CDS, and that's what I focus for now. And yeah, I'll leave the other parts for the long talk or the paper. So what's the conditional disclosure of secrets primitive? Again, it's a two-party primitive where we have a sender who chooses an input to an NLP relation and a message M. The receiver then chooses a witness from a candidate witness for this NLP relation, and then receives back some message M prime. And what we want is that M prime is equal to the message M chosen by the sender, if and only if X and W belongs to this NLP relation. or the receiver receives abort otherwise, or perp. We need an extra property from these CDS protocols. In particular, we need it to be verifiable. So we say that the protocol is verifiable first if it implements this ideal CDS functionality. And on top of that, we want that the classical transcript of the protocol somehow binds the message M chosen by the server. So in more details, what we want is that there exists a verification algorithm Ver such that the the sender can output a proof pi, such that in the honest case, this verification procedure passes on the classical transcript of the protocol, the input to NP relation, the message chosen by the sender, and this proof pi output by the sender as well. And like the stronger requirement that we want is that this is binding, showing that for every malicious sender, they cannot choose a message and a proof that pass the verification algorithm if this message wouldn't be the one that would be open for the verifier. Sorry, for the receiver. And this is just a quick overview of how we use this unbounded simulator VCDS for extractable commitments. And the main point is that we can we can set up we can use a chapter setup phase where the receiver commits to 0 and then prove that she committed to 0. And then the committer and the receiver, they run this VCDS protocol for the language where you have commitments of 1 and the randomness used to the commitment of 1. And in this here, the idea is that the committer will choose the message M that will be committed later in the protocol. And the receiver should give the randomness for the commitment of 0 that she sent in the first message. But as you see, like in the real protocol, the receiver committed to 0, so she cannot give a randomness R that is a valid witness for this language. And therefore, in the real protocol, the receiver won't learn the message M, and we have the binding, the hiding property of the commitment scheme. On the other hand, when you consider the extractor, this extractor can then rewind, so we can use the zero-knowledge simulation and change the commitment to 1. And in this case, running the VCDS protocol, the extractor will be able to learn the message from the honest run of the VCDS protocol. Just to conclude, so what we show, the main message of our result is that we can have a secure multi-party computation in Minikube, so in the world with quantum and one functions. And moreover, we can show that if you have access to a CRS, then we can achieve this protocol in constant rounds and that its use is secure. I think the main open problems that are left is, okay, what else can we do in Minikube? So what else can we do from one functions in the quantum world? Or we can go a step further. Can we do more things with access to public encryption in the quantum world? Or on the other hand, can you prove separations? Can you show that some primitives cannot be implemented in either of these worlds? And with that, I'd like to thank you for your attention.
Thank you very much. Any questions? A bit early in the morning, I guess. I have one question. Do you have any conjectures about separations? Like any candidates that you think might not be one-way functionable?
Okay, one conjecture, for example, is quantum key distribution with classical communication. So this is a conjecture that it is not in Minikube, for example. And you can also think about, I don't know, this very strong crypto like obfuscation or everything. It should not be able to done with be able to be implemented with quantum, even with a weaker, classical crypto primitives.
Okay, cool. Thank you very much. And now we can come to the next talk. I guess I need to hide those slides first. Where is it? Where's the? Down there. Yeah. Okay. Thank you. Okay. So on our side, we seem to be ready now for the next talk. So the next talk is a security analysis of quantum lightning by Bhaskar Roberts. Are you online?
I do not see them.
Okay, so I guess that we then switch the talks around, maybe if we can, and see whether Bhaskar will appear again. So how about Takashi? Are you online and ready?
Yeah, sure. Then can I start?
Yeah, so I will announce the talk, and then you can start.
Okay.
So the next talk will be on classical versus quantum random oracles by Takashi Yamakawa and Mark Gendre, and Takashi will be giving the talk. It's your stage, please.
And thank you for the introduction. So I'm Takashi, and I will talk about classical versus quantum random oracles. And the random oracle model, ROM, is a widely used model of cryptographic hash functions. In the model, some random function is chosen at random at the beginning of some security game, and adversary is allowed to make queries to the random function in a black box manner. And this model is widely used for analyzing various kinds of practical cryptographic schemes. And the quantum random oracle model, QROM, is the quantum version of the ROM. The difference is that adversary is allowed to make quantum queries to the random oracle. And the reason why we should consider such a model is that in the real world, we replace random oracle with real world hash functions. And if adversary has a quantum computer, then he can use the quantum computer to evaluate the hash function. And this corresponds to quantum access to the random oracle. And so we should consider QROM for ensuring post-quantum security. And after the introduction of the QROM in 2011, there have been a lot of study about the QROM. And now we know that almost all major protocols in the ROM are actually also proven secure in the QROM. And now there is no known scheme that is secure in the ROM, but insecure in the QROM before this work. So it is natural to ask the following question: does security in the ROM imply security in the QROM? And if this is true, this is very nice, because this means that we do not need to consider QROM, and we can just focus on the ROM, which is much simpler than the QROM. And this is our results. So we give both positive and negative results, negative answers to the question. The first is the negative answer, which gives the first separation between the ROM and the QROM. And especially we give constructions of PKE and signature schemes that are secure in the ROM, but insecure in the QROM. And I remark that a similar result was also shown in the concurrent work by Zhang et al. And our second result is a positive result. We give some ROM to QROM lifting theorems under some conditions. So let me explain more about our separation results. So for giving the separation, we introduce a new primitive, which we call proof of quantum access to random oracle, POQRO. So this is an interactive protocol between quantum prover and classical verifier, where the prover proves that it has the quantum access to the random oracle. And one may think that this is similar to the notion of proof of quantumness introduced by Blaketsky et al. But the difference is that we require soundness against even quantum cheating prover as long as it only has classical oracle access. And on the other hand, in the POQ, the soundness is only required to hold against completely classical cheating prover. So this is the difference. And we give two constructions of POQRO. The first is privately verifiable construction from LWE. And actually, this is exactly the same construction as the proof of quantumness by Blaketsky et al. So our contribution here is the observation that their protocol actually also satisfies soundness as POQRO. And by using such a privately verified POQRO, we can get separations for EUF, CMA signatures, and InCC PKE by just embedding the verification of POQRO into signing or decryption algorithm of these primitives. And our second construction of POQRO is relative to some artificial classical oracle inspired by the recent work on one-shot signatures by Amos et al. And the nice feature of this construction is its public verifiability. And by using public verifiability, we can get separations for weaker security notions for signatures and PKE. And finally, let me explain our lifting theorem. So for our lifting theorem, we consider the following type of games. So that in this game, we consider interaction between quantum adversary and classical challenger. And suppose that challenger makes at most k queries. Then our listing theorem states the following. So for any A making q quantum queries, there exists B making k classical queries, such that this inequality holds. And especially when k is constant, this factor is polynomial. Therefore, we can say this. So if B's winning probability is negligible, then A's winning probability is also negligible. And in particular, B only makes classical queries. So this can be seen as a security in the ROM, and this can be seen as the security in the QROM. So this is why we call this theorem as a lifting theorem from ROM to QROM. And let me remark that this theorem is meaningful only for such type games, because for indistinguishability-based applications, adversary advantage is this probability minus 1/2 rather than this probability itself. And so this theorem is not meaningful for indistinguishability-based application. And this is why we focus on such type games for this theorem. And that's it. Thank you for your attention.
Thank you for your talk. Are there any questions from the audience? I have one question. Could you just for kind of clarity, give an example of a search type game, like a normal, a natural cryptographic security notion, for example, that could be lifted?
For example, the soundness of non-interactive zero knowledge can be captured.
Okay, thank you very much. So quickly checking whether Bhaskar Roberts has shown up in the meantime.
I do not see him, and I sent him an email. I believe that he's at UC Berkeley, so it's after midnight. He may have fallen asleep.
Yeah, or it could be technical connection problem. So let's, then they would probably look at the email. Well, let's check at the very end of the session again. Is Yu Xuan available?
Yes, I'm here. Can you hear me?
Yes, I can hear you. I will announce your talk. So
okay, maybe I'll share my screen.
Yes, please do. So the next talk will be on the compressed oracle technique and post-quantum security of proofs of sequential work by Kai-Min Chong, Serge Fair, Yu-Xuan Huang, and Taining Liao. And Yu-Xuan will be giving the talk now. It's your stage, please.
Thanks for the introduction. Can you see my slides?
Yes.
Okay. Hi everyone, I'm Yu-Xuan Huang. Today I'm talking about work on the compressed oracle technique and post-quantum security of proof of sequential work. And as mentioned earlier, this is a joint work with Kai-Min Zhong, Serge Fier, myself, and Taining Liao. So first, we're going to talk about the quantum random oracle model. The random oracle model is a common way to analyze classical cryptographic schemes that use a hash function. Here, hash functions are idealized into uniformly simpled function that everyone has access to. We are also putting this into the quantum settings where now we can make the query in superposition. Also, we are in the setting of parallel queries in which multiple data points can be asked for a single query round. A typical example problem in the random oracle model is a zero preimage problem, which asks to find the input that is mapped to 0. And it is well studied in both classical and quantum settings. So what have we done? We offer a useful framework for analyzing such problems in parallel query quantum random oracle model. Using our framework, one can prove quantum hardness of these problems using classical reasoning. And this works by recycling probability bound from classical proof and lifting them into quantum proof if in suitable form. Independent and concurrent to our work, Blocky et al. Also managed to tackle one of our applications, the post-quantum security of PSW scheme or proof of sequential work scheme proposed by Cohen and Piatrak in 2018. However, their proof is tailored to the specific problem, whereas our framework is generally more applicable into solving various example problems. And also to understand their proof, a certain amount of quantum information science is required, while assuming our framework is correct. Verifying our proof is just a matter of purely classical reasoning. So next, let's talk about the lazy sampling, which is useful in analyzing hard problems in the random oracle model. Instead of sampling the entire random oracle in the beginning, we can simulate the random oracle using a database that is initially empty, and whenever an entry being queried, we sample the fresh randomness for that entry. For analyzing the zero preimage problem, we observe that if after like Q queries, the obtained database contains no 0 within the sum of its entry, then the adversary is unlikely to output 1 zero preimage neither. And this can be formally written down as in following formal bound. Putting this into the quantum settings, now the database are in the quantum superposition state, and we have similar observation except with different formal bound here. So next, let's see the classical analysis of the zero preimage problem, and keep in mind that our goal is to eventually lift them into quantum proof using our framework. So how do we, for example, show that to bound the probability of database having a 0? First, we observe that if after Q sequential queries, the database acquires a 0 within some of its entry, then the 0 must occur within one of the sequential queries. We can therefore bound the desired probability by summing together this bracket notation we called the transition capacities. And second, we observe that if after one parallel queries, the database acquires a 0 within some of its entry, then that 0 must occur one of the queried entries. Putting things together, we can now bound the desired probability. And for the second observation, we are using the terminology that the transition of database shifting from not having a 0 within some of its entry to having a 0 is recognizable by local properties 0. And we refer to this property 0 being local because it only depends on one entry of the database. And putting this into a high level, we have the following recipe, which first, we decompose the probability into sum of transition capacities, and second, we bound the transition capacities using probability of local properties that recognize the transition. And in our framework, we have pretty much the same recipe, except now we're in the quantum settings, so different definition of the transition capacities and corresponding adjusted formulas. But the point here is it's just a matter of recycling probability bound from classical proof and plugging into our formulas to obtain quantum bound. And we can finally lift the classical analysis into quantum analysis. And the punchline here is we don't need to understand the definition of transition capacities. We can simply lift them into quantum proof. By using the same recipe, we obtain several additional results, including hardness for collision finding problem and for keychain finding problem. As a main application, we also give the post-quantum security proof of the non-interactive variant of PSW scheme proposed by Cohen and Piatrak in 2018. So the PSW scheme is a useful cryptographic primitive in the context of blockchain, in which prover tries to convince the verifier that a certain amount of sequential computational work has been done by prover. But here the situation is more complicated because we need to consider intertwined core problems within the PSW scheme. So we need tools to decompose these complicated transition capacities into simpler forms. That's why we are giving the calculus for transition capacities, and this allows us to work with these capacities on an abstract level without understanding the definition, and from which we can have a simpler form of transition capacities and use of our previously mentioned recipe for the rest of the analysis. So finally, let's recap on our contribution. We offer a useful framework that, whenever applicable, help us prove query complexity bound in the parallel query quantum random walker model. And this works by purely classical reasoning that lift classical proof in the quantum proof if in suitable form. Yeah, and finally, we encourage the audience to refer to our paper for more detail. And we thanks for listening.
Thank you very much for your talk. Are there any questions in the audience? Yes, we have a question. Yeah, please find a microphone.
So are these techniques also applicable when a protocol is using multiple QROMs? So let's say there are two QROMs in a protocol. So are these techniques?
We are in the setting of where we only have one QROM, but if you want to have multiple QROM, I believe you can simply sample different prefixes in the random walker model. Does that make sense?
Right, right. And is there like a composition theorem between multiple QROMs that we can use?
The original formulation of Zendry does not, I believe, does not include multiple random walker maybe. So, but potentially, I think it could be because, yeah, since it's just a matter of sampling different prefixes for the random walker. Does that make sense?
Yeah, okay, yeah, thanks.
Okay, any other questions? I just noticed that I never checked whether there are questions online. Is there someone who would remind me of that? Is there someone checking online questions? Because I don't have access to them.
I have looked. There are no questions in the Zulip chat and none on the Zoom chat.
Okay, will you let me know if there are questions?
Yes, I will.
Okay, thank you. Good. Then let's thank the speaker again.
Thank you.
And now, Tina Zhang, are you available?
Sorry. Yes. Hello.
Okay, perfect. So then we can, you're ready for your talk? Yeah, early, but okay. So the next talk will be Classical Proofs of Quantum Knowledge by Tina Zhang and Thomas Widig. And Tina will give the talk. And it's your stage. Please share your slides.
Mm-hmm. Okay.
Okay, we see your slides. Thanks.
Okay, thank you. Thanks for the introduction. So I'm going to tell you briefly about classical proofs of quantum knowledge, which were the subject of this joint paper with Thomas Widig at Caltech. So there were three main points which we wanted to address in this paper. We are interested in proofs of knowledge where the prover is quantum, but the verifier is classical and the witness is a quantum state instead of classical string. So briefly, a classical proof of knowledge protocol is a protocol that, informally speaking, lets a prover prove to a verifier that it knows some witness for some MP instance. So for example, that it knows a 3 coloring for some particular graph. We're interested in defining these objects in the setting where the prover wants to prove that it knows a quantum state instead of a classical witness. And after we define these objects, where we prove some interesting properties of that definition that have relatively simple proofs, and then we provide some examples that instantiate the definition, and in so doing, introduce some techniques that might be useful for generally analyzing protocols like this. So what's the difficulty in defining classical proofs of quantum knowledge? Why can't we just translate the classical definition to the quantum setting? There are two hiccups. The first is that uniquely quantum applications, such as quantum money, which is one application we consider, don't always fit well into a formalism that was originally designed with sort of classical applications, such as classical public key encryption in mind. So the classical definition is kind of motivated by this imaginary scenario where you have a prover who wants to prove to a verifier that it knows a secret key, for example, for some publicly known PK public key. And that's formalized by encoding the public key as an instance of an NP-complete problem. And you encode then the secret key as a witness to that instance, and you have some public relation R, so just a function which determines whether instance witness pairs are valid. So that makes sense for classical public key encryption schemes. So this is an example with Diffie-Hellman of how you would set it up. It makes less sense for something like quantum money, where it's also a setting where you intuitively have a prover wanting to prove to the verifier that it knows or has something. So in this case, it's a quantum money state. But that situation doesn't fit too well into this formalism, which was developed for classical purposes, even if you replace all of the classical MP things with their quantum, so QMA equivalents. So that's one difficulty in settling the definition. There's also the question, what does black box access mean when you have a quantum prover who only outputs classical strings? So usually the security property of proofs of knowledge, which intuitively should say something like, the prover only passes in this protocol if they actually know the witness in some sense. Usually this intuition is formalized by saying that there should be an efficient extractor that can output the witness after looking only at the input-output behavior of the prover. So the intuition is that the prover must have really known the witness if it's possible to pull it out of them by interacting with it in this black box fashion. But generating some quantum witness by only looking at classical messages, remember we're interested in the classical verifier setting, so the messages must be classical. That seems as hard as quantum state tomography. So black box access, if an efficient extractor is going to do anything useful, needs to be a little bit different in the quantum world. So I cover how we overcome these hiccups in the full talk. And we also prove these. So once we settle the definition, we prove these properties, of which there are some informal statements here. So the first one is that a non-destructive proof of knowledge, so one that does not destroy the witness state that the prover is using, so that the prover can repeat the protocol as often as it likes. Such a proof of knowledge for some witness state implies that the state can be cloned by an unbounded adversary. So that has consequences in the quantum money setting, because often quantum money schemes are information theoretically secure. And the second property is that proofs of quantum knowledge can be used as quantum money verification protocols. And we formalize what that means. And once you see the formalization, it is rather an intuitive thing to expect. And once we have a definition and we have some properties of it, we also want some examples to show that there really are protocols that instantiate the definition, and also to come up with some techniques that might be useful in analyzing said protocol. So the most, well, we do 3 examples in the paper. 2 of them are kind of similar. They're both based on information theoretically secure quantum money schemes that have classical verification. And one is computational. It's based on the Mahadev 2018 verification protocol for BQP. And so I think the most interesting technique here is this one which we use for the information theoretic quantum money schemes, where we actually borrow from the self-testing literature. And in order to be able to apply it, we interpret a quantum money verification protocol. So it happens to have classical communication. So, the prover is challenged by the bank and replies with classical messages to prove that it had a quantum money state. We consider such a protocol and we interpret it as a non-local game, so that then we can apply a rigidity theorem in order to completely characterize the prover based on its classical input-output behavior. And that characterization kind of lets us know what the prover is doing and allows us to find the state, the witness state, the money state we're interested in inside the prover's registers, given the sort of black box access that we're allowed in the quantum setting. A priori, the internal registers with prover don't have any particular structure that we can exploit, but the self-testing theorem is powerful enough to give us enough structure to actually recover the money state from the prover if it passes with high probability in the protocol. So that's probably the most interesting technique here. The Mahadev proof actually goes forward pretty straightforwardly because most of the technical ingredients that we require were already in her paper, and we just make the claims explicit in order to show that they satisfy our definition. So that's basically all I wanted to say. Thank you for your attention, and I'm happy to take any questions if there are any.
Thank you for your talk. Any questions from the audience? Yes, we have one question.
Hi. So the extractor in this proof of knowledge, does it also preserve the final state of the prover along with extracting the witness?
Does it preserve the final state of the prover?
Yeah, for example, if this proof of knowledge has to be used in a larger protocol, then the extractor in the proof would have to preserve the final state of the prover in order for the reduction to go through.
So the extractor, I guess you're referring to which protocol, the Mahadev or the self-testing one?
Anyone. I mean,
Okay.
like is the what I'm trying to ask is when we run the extractor, the final state that the prover ends up with is the joint distribution of that state and the witness indistinguishable from the actual real world final state of the prover and the witness?
I see. So the extractor is in the quantum, in the self-testing case, at least, this extractor is an isometry. So whatever you did, you could undo it, presumably. In the Mahadev case, I am not sure. Yeah, I'm not sure. I would have to check.
Okay, thanks.
Thank you. Any other questions? Okay, then let's thank the speaker again.
Thank you.
And this is the last call for boarding for the quantum session. Passenger Bhaskar Roberts, please report to the gate.
I do not see him online, and I have not received a response to email.
Okay, so then we need to unload the luggage. Let's thank all the speakers from this session again. And I wish everyone a happy coffee break and the remote participants something like it. Goodbye.
We shall